Hi, my name is Grant McKinnon, and I want to talk about basic MRI principles and how to apply some of these principles when looking at different MRI sequences. At the bottom of our screen, we have a MRI of a tomato, and I hope by the end of this talk you'll have an appreciation of how the sequence was obtained and how to identify it as being a T2 sequence. So to think about MRI physics, we have to take a step back to our general physics and think about the relationship between current and magnetism. If you have a straight wire and you apply a current through it, you will produce a magnetic field circular and perpendicular to the current. So if we use our right hand rule, where our thumb is in the direction of the current, our four fingers will wrap around the current and show the direction of that magnetic field. So on our screen, we have an example of current flowing from south to north, and the magnetic field is being produced counterclockwise. So we can apply the similar principle if we think about wire loops. So if you have a wire loop and apply a current through it, the magnetic field produced will be perpendicular to the loop. So we can use our right hand rule, where now our four fingers are going to be the current, and the magnetic field is going to be our thumb. And when you do this, if you look at our example to the left here, I, which is our current, is moving counterclockwise, and applying the right hand rule, you'll see that the magnetic field is going to be produced south to north. If we think of all the hydrogen protons in our body having a positive charge and them spinning, they're acting as a pseudo wire loop. They're producing some sort of current. And the current that is produced is also going to produce a very small magnetic field. And so, like the example on the left, this hydrogen proton is going to produce a very small magnetic field from south to north. So each MRI has a Tesla magnet that the magnetic field is produced by a series of high current coils that are in wire loops. And so the main magnetic field is going to be produced by these wire loops and be perpendicular and in the south to north orientation. And so if we think of these coils being in the tube that the patient goes in, the patient is going to be lying in the south to north orientation. So if we look here on our left, the main magnetic field goes typically from the patient's feet to their head, but it can also go from their head to the feet. And we call this orientation the longitudinal direction and the z-axis. And so everything is 3D, and so we have two other axes. We have the x-axis and the y-axis, and together they will form the transverse plane. And the transverse plane, if we think about our patient lying in the MRI scanner, the transverse plane is going to be an axial plane through that patient. So these are very important principles. We're going to be talking about the z-axis being longitudinal, and then the xy plane being the transverse plane. So like I mentioned, all of our protons are going to have some sort of magnetic field that they produce. And when there's no external magnetic field, when the patient is out of the scanner, the individual proton magnetic vectors are very random, and they're essentially canceling themselves out because there's an infinite number of hydrogen protons in an infinite number of orientations, and they will all cancel themselves out. However, when you apply an external magnetic field, the proton vectors in each individual proton will align parallel or anti-parallel. More protons will align parallel, so the sum of the vectors in the z-axis is going to be parallel. Now remember, the magnet in the MRI scanner is always on. So our protons will always want to relax back to the z-axis in their parallel or anti-parallel direction. So I want to talk about a principle called precession. If you take a spinning top and you spin it on a table, we can think of that as kind of being our hydrogen proton spinning. But the top will also have this wobble aspect to it, and this is due to the top spin and gravity. So similarly, a hydrogen proton will precess, it will wobble due to its spin and the magnetic field produced by the scanner. So the important part for MRI physics is how many wobbles occur per second. And this is called the Lamar frequency. And so this is really, really important because this is how we add energy to the proton. And this will drive our discussion in the next few slides. So I'm going to talk about this principle a little bit more. So the Lamar frequency is a linear equation where the frequency is equal to the gyromagnetic ratio times the main magnetic field strength. And so in most scanners, the magnetic field is 1.5 Tesla or 3 Tesla. And the gyromagnetic ratio is just purely a constant that's unique for that atomic nuclei. So for hydrogen protons, the constant is 42.6 megahertz per Tesla. And so in a 1.5 Tesla MRI, the frequency is 64 megahertz. So if you've ever pushed a kid on a swing, you'll know that you transfer energy best when you're pushing at the same frequency as the child and at the correct position. You don't want to push when they're coming back to you. You want to push when they're going away from you. So like pushing a child, we want to add energy to our protons at the same frequency that the protons are precessing. And if we do that, if we add energy at 64 megahertz that we calculated in this last precession, we would be in resonance. So this is very important on how we add energy to protons. And when we do that, it's called radio frequency energy. And so how we produce this energy is we rapidly change electrical currents at a specific frequency, meaning 64 megahertz for most magnets, and this will transmit energy to those protons. And so the energy transmitted is not by our main magnet. This is transmitted by a transmit coil. And so these are going to be specific coils that go on the body part of interest, such as a head coil or a knee coil. And this energy is transmitted in a very pulsatile fashion, meaning that the energy is added and then taken away. So just an interesting side note is the Lamar frequency of most hydrogen protons with a 1.5 Tesla magnet, like we saw, was 64 megahertz, and the radio broadcast of 89.9 FM is 89.9 megahertz. So all radio waves should be shielded from MRI magnets. So at the Lamar frequency, an RF pulse allows protons to absorb this energy. Now, what does the proton do with that energy? So when you provide energy, it will allow that proton to move away from the resting state. So here on our left, we have the resting state of a hydrogen proton. We're going to add a little bit of energy, and you see that we translate away from the z-axis. If we add enough energy, our z-axis component can actually go all the way to 0. And now we are completely in the transverse axis. And so the amount of angle that we have after a certain RF energy pulse is called the flip angle. So this is a 90-degree RF pulse because our flip angle is 90 degrees. So now we can start getting into some of the fun stuff. So after a 90-degree RF pulse, the z-axis magnetic vector is 0, as shown here on the right. Once that RF pulse is removed, the vector will align back to the z-axis, because remember, the magnet is always on. The external magnet is so much stronger than the magnetic force of our individual hydrogen protons, so they will want to go back to the relaxed resting state. And so this is termed T1 relaxation, and this is the longitudinal relaxation because it's going back to the longitudinal z-axis. And so the amount of time that it takes to have a longitudinal relaxation is different for hydrogen protons in different tissues. So that's how we can tell that this hydrogen proton is from water, whereas this hydrogen proton is from fat and with an infinite number of other tissues. So if we look at this image here on the left, we have our resting state where our proton magnetic vector is in the direction of the z-axis. After we give an RF pulse, we provide a certain amount of energy that we go all the way down to this resting state where we have Z equals 0 contribution. And then once we remove that RF pulse, that RF energy, we're going to start to grow back some of our longitudinal Z-axis component. And so this here is longitudinal relaxation, and this is T1 relaxation. Of note, the amount of energy and the amount of magnetic vector you have here is going to be less than the magnetic vector you have here, because remember, we added energy. So the energy state is going to be higher after doing this RF pulse. And when we think about a specific tissue's T1 time, that T1 time is the time it takes after removing the pulse for that Z-axis to get back to 63%, the maximum amount. So this 100% here is not the original Z-axis component. It's the final Z-axis component. And so the T1 relaxation, or the T1 time, is going to be the time it takes to get to 63% of that maximum value. So here on our left, we have an axial slice of a brain MRI. And we have some tissues that appear bright and some that appear dark. The bright tissues have short T1 times. So this is going to be fat, subacute hemorrhage, melanin, gadolinium, or other paramagnetic metals such as iron, and proteinaceous fluid. Now, dark materials will have a long T1 time, and these include water, calcifications, and flow voids of our major vessels. And this graph here on the bottom shows the longitudinal magnetic vectors and how they change over time. So we can see that the white matter has a shorter T1 time compared to the gray matter, which has a shorter T1 time to the CSF. Now, T2 relaxation starts also with a 90-degree RF pulse. So here's our normal resting state. We give the hydrogen protons a 90-degree RF pulse. So this is exactly where we were with T1. Now, when you give an energy by an RF pulse, all the protons begin to precess together in phase. And so this means that they are not just spinning at or wobbling at the same frequency, but they're wobbling at the same point in that 360-degree axis altogether. And then after that RF pulse is taken away, the protons begin to precess out of phase. And this is due to spin-spin interactions, which is beyond the scope of this talk. But when they start to precess out of phase, they start to move away from one another, and they start to equilibrate with having 0 transverse axis component. So if we look at this point in time, all of our magnetic vectors are in the positive y-axis here, or the xy axis. And once you remove that energy, they will start to equilibrate, and they will have a 0 transverse axis component. And you might be thinking, how do we measure the amount of magnetism? And how we do this is we have a coil that is perpendicular to our magnetic vector of interest, so the transverse axis in this example. And like current can produce magnetism, the opposite occurs as well. So magnetism can produce current. So the magnetic vector here is going to produce a very small amount of current that we can measure. So we can measure the transverse component of that magnetic vector. So I just want to briefly touch on T2 and T2 star. So they essentially are cut from the same stone. T2 star has 4 different contributions that lead to dephasing, whereas T2 dephasing eliminates 3 of these contributions and only focuses on the spin-spin interactions. So essentially, they are markers of the same relaxation, but just with different sensitivities. So T2 relaxation is a little different than T1 relaxation time, because our T2 time is the time it takes to go from 100% transverse component down to 37% transverse component. And so this T2 time for is very dependent on the hydrogen protons in different tissues. So here on our left, we have a brain MRI in the T2 sequence, and we see the obvious differences between our T1 sequence. So now what's bright is water and fat, and now what's dark is calcification, proteinaceous fluid, the paramagnetic substances such as gadolinium and iron, and flow voids. Now note the change here. So previously bright was short T1 time, but now bright is long T2 time. And so the graph here on the bottom just shows the transverse magnet vector over time, and then we see that white matter has a shorter T2 time than gray matter that has a shorter T2 time than CSF. So inversion recovery is a really cool way that we can eliminate some of the signal from a specific tissue of interest. So we typically see this with fat suppression, but in neuroimaging, we often see this with FLAIR, where we're reducing or eliminating the contribution from the CSF. So I'll talk about this just because I think it's pretty cool. But what you do is you use a 180-degree RF pulse prior to a 90-degree RF pulse. And I think this slide displays that a little better. So here we have our resting state. You have a certain voxel, which is a certain amount of area of interest, that has the sum of the magnetic vectors in the positive z-axis. Now, for simplification, we're going to say that of the tissue in the voxel, some of it is fat and some of it is not fat, or just any other tissue. But they all will have a sum of being parallel to G. So they will also all have positive z-axis components. Now, after you give a 180-degree RF pulse, you're going to move them from this position all the way down to this position. Now, like I mentioned, T1 relaxation, which is our longitudinal relaxation, is very dependent on the tissue type. So what we do after we remove the pulse is we watch the tissues, the magnetic vectors, start going back to 0, z equals 0, and then start moving towards the z equals positive axis. And fat will have a shorter T1 time, so it's going to it will more quickly get to the z equals 0 axis. And when it does that, eventually there will be a time where it has a z equals 0 component, but all the other non-fat tissues are still relaxing. So they're still in the negative z axis. So what you do now is you do a 90-degree RF pulse. And when you do this pulse, all the tissues are going to move to the 90-degree transverse axis, but then fat, which was at z equals 0, remains in the transverse axis at z equals 0. And so you essentially eliminate all of the fat contributions. So in summary, I hope this didn't muddy the water when thinking about the MRI different sequences, but Dr. Peter Mansfield and Paul Lauterbur well deserve their Nobel Prize for inventing the MRI. And MRI physics can be very intimidating, but not many people truly understand MRI physics. So don't feel bad, and maybe revisit this lecture in the future to hopefully address some of the questions that you might have. Here are my references, and I hope this was helpful. Hope you have a great rest of the day.